So last time I was telling you a story of the birth of the modern chemical industry and dye molecules and how that was related to a surge in organic chemistry research and the concept of chemotherapy. So about the time that dyes were discovered, and here is one of them, this one's called methylene blue. You can tell it's highly conjugated, aromatic rings, and that high level of conjugation makes them absorb visible light, and that's where we see color as the wavelengths that are not absorbed get reflected. Anyway, chemist Paul Ehrlich was using methylene blue to stain cells. He was doing what's called histochemistry, which is where under a microscope, if you look at unstained cells, there's not a lot of contrast, but sometimes if you use a dye, the dye will be selectively taken up by some portions of the cell and not others, and you get more contrast, more ability to see the image. And he was doing this and sort of had a light bulb moment when he thought, what if I use this to try to kill cells that I want to kill? And he was thinking specifically about parasites. So there's a parasite called Plasmodium, and he had noticed that this drug, this molecule stained the parasite, and he thought, can that actually kill the parasite? And it worked. And thus was born the idea that you could use a molecule to target a specific organism and kill that organism. Now, that's a tough sell, and some of these molecules are not very selective. Ideally, you want a molecule that kills a pathogen or a cancer cell, but not a cell that's good and doing its job. And that's the modern story of drug development and cancer chemotherapy, searching for molecules that can selectively target various diseases. But that idea all sort of started there. And a lot of people got on board with it, not only in synthesizing dye molecules, but in using those dye molecules as potential medications. So here is one. This is a dye molecule called trypan red. And you can see that it's got some unusual linkages between nitrogen molecules. Those are called azo linkages. And we're going to learn how to make those linkages today. The cool thing about azo linkages is their synthesis is totally modular, meaning you can synthesize one side and then another side and bring them together at a late stage. And so you can see that they've done that here. And that allows you to mix and match portions of the molecule to test hypotheses, like if I made some changes here, would the dye be a different color? Or if I made some changes there, would the dye more effectively target a pathogen? This one happens to kill trypanosomes, which are responsible for sleeping sickness. This is another dye molecule that instead of nitrogen has arsenic. So that sounds like a bad idea because you know that arsenic is poisonous. But if you look at the periodic table, it's a couple rows down from nitrogen, has the same number of valence electrons. And so they were able to make this sort of azo-type compound with arsenic. And this one kills the bacteria responsible for syphilis. It's an anti-syphilitic, and at one point was one of the most prescribed drugs. So a lot of interesting development. Now, if we have time later today, I will tell you how a dye molecule based on an azo compound, led to the development of sulfa drugs just immediately prior to World War II. It probably saved a lot of lives by being able to fight infections among injured soldiers during World War II. But before we get there, we want to just talk about some basic chemistry. So first, we're going to talk about making a class of molecules that are new electrophiles. A new electrophile, and that electrophile is going to be called a diazonium salt. And we're going to be able to do some interesting things with the diazonium salt, including make azo compounds that are useful as dyes. So to get started, making a diazonium salt starts with aniline. Just to remind you, you can make aniline from benzene using a pretty straightforward two-step procedure. You do the nitration reaction first to install a nitro group. And then in a second step, you do the reduction reaction with hydrogen and palladium on carbon to reduce the nitro group to the aniline. So that's not new, that's review. But there's a new reagent called NaNO2 sodium nitrite and HCl, and that will convert the aniline into the following group, which is called a diazonium salt. This group has the nitrogen of the aniline here, and then the nitrogen of sodium nitrite here. They come from those sources. But now they're combined together into what you might expect is a super good leaving group. And we call this a diazonium salt, and it usually has Cl- as the counter ion. This process of making a diazonium salt is sometimes called diazotization, which is a big word, and you don't necessarily need to know it, but you may hear people or organic chemists refer to it. So I want to show you just briefly the mechanism for making the diazonium salt. Sometimes I remember not really understanding this mechanism or this reaction as a student. I don't think we learned the mechanism. And back then, I felt like if I didn't know the mechanism, then it wasn't important and I didn't need to know it. And that actually lost me some points on an exam because I didn't know this reaction. The mechanism is available in your text. It's not too hard and it's not the most important thing in the world, but I did want to show it to you to help you remember what this reaction does. So to begin with, sodium nitrite looks like this with a lone pair on the nitrogen. Now, in the presence of HCl, you could imagine protonating that oxygen. I'm not going to show you that mechanism. Presumably, you can do that. The negatively charged oxygen would steal a proton from HCl. And if we had an excess of HCl, you could imagine lone pairs on that oxygen getting protonated again to turn what used to be a negatively charged oxygen into a good leaving group. And then you could imagine lone pair electrons on the oxygen kicking down to do an elimination reaction where they kick off the leaving group. That generates the important electrophile for the diazotization reaction. And this is called a nitrosonium ion. And it has a resonance structure where the positive charge is on the nitrogen instead of on the oxygen. You get to that resonance structure simply by moving the lone pair, moving the electrons from one of the two oxygen-nitrogen pi bonds out onto the oxygen. Oxygen's more electronegative than nitrogen, so you would predict that this reagent is electrophilic on the nitrogen. And so what happens in the diazotization reaction is lone pair on the aniline attacks the electrophilic nitrogen to make a new nitrogen-nitrogen bond. And if you look at the product, we need 3 bonds between nitrogen and nitrogen. We just made one, the sigma bond. Now we're going to need to make 2 pi bonds. And effectively what's going to happen next is some tautomerization reactions. So remember, tautomerization is all about moving where protons are and moving where double bonds are. So just follow this through. In the 9 a.m. hour, some people were asking, why are you protonating there as opposed to these other places? And the answer is, certainly you could protonate on any of those lone pairs, but what I'm going to show you is the tautomerization reaction that leads to the product. You wouldn't be required to predict that this would happen, but knowing that it does, this mechanism shows you how to get from A to B. So probably the first thing is that HCl protonates the oxygen, lone pairs on the oxygen. So that's sort of the first in our step of tautomerization reactions. By the way, there isn't a lone pair on that aniline. I'm surprised somebody didn't say something. There was muttering, so maybe you were disgusted. Is that better? We all okay there? Texas nitrogen, sorry. Yeah, what's the reference to Texas? So organic chemists call atoms that have too many bonds Texas carbons or Texas nitrogens, because even though Texas is such a big state, even carbon is not bigger in Texas. I don't know. Yeah, it's not really particularly funny. So last night I picked up a new dad joke in the Special Needs Mutual. It was great. I learned it so we were going to start, our opening hymn was Let Us All Press On, and the lady who was conducting said, we're going to sing a song about salad. And everybody was like, what? Let us all press on? Isn't that great? Yeah. Yeah, my sons would rank that as sort of 2 or 3 out of 10 on the dad joke scale, which is the sweet spot. That's what you're going for. So mission accomplished. All right, so having protonated that oxygen, then a base, probably Cl-, not a particularly good base, but that's fine. We'll do the tautomerization step where you remove the proton from the nitrogen and create a new nitrogen-nitrogen pi bond, breaking an oxygen nitrogen pi bond and getting us to, and there should be a positive formal charge there, sorry, getting us here. Right? I didn't do anything wrong, did I? I'm trying to remember. Okay, I am screwing this up a little bit, but inconsequentially, so your text is going to deal with the proton transfer steps a little bit different. I'm not going to erase things. We're just going to move forward. All right. So we get this intermediate where we now have a nitrogen-nitrogen pi bond and an OH group. I'm going to skip ahead because, fine. I don't want to spend too much time on this because this is not the most important thing. If we protonate the oxygen, then we turn it into a good leaving group. And the final step that generates the nitrogen-nitrogen pi bond is this one, where electrons on the nitrogen kick down and kick off water, and then that gives you your diazonium ion. Okay. For full disclosure, I think what I was supposed to do here was remove a proton off the aniline first and then protonate on the oxygen. What I've shown you here works fine. I'm clearly not going to test you on this if I screw it up in class. I mean, that's probably not right, but I did want you to have a sense for how this reaction works. Okay, so what do aryl diazonium ions do? What are they good for? And the answer is as electrophiles. And we'll use them as electrophiles in 2 different reactions. One of them is new, and the other is just a variation of something that you've seen before. Oops, I meant to use the word electrophile. So we're going to use them as electrophiles in a new kind of reaction called nucleophilic aromatic substitution. This is going to be different from what you learned in Chapter 20, because in Chapter 20, the benzene was always the nucleophile. Here, it's going to be the electrophile. And the reason it's an electrophile is because, as I said, the thing we just made with the 2 nitrogens triply bonded to each other is an exceedingly good, three E's for exceedingly good leaving group. Back when my kids were younger, we used to, when we were occasionally, we were not the best at reading scriptures together. We did make an effort, and I would try to make it fun. And Nephi uses the word exceedingly. So I would just draw it out, exceedingly. So I always want to do that. Then one of my sons decided we should start pronouncing punctuation. And so then, and it came to pass that I, Nephi, said colon. or semicolon, anyway. So, how old was this kid? I don't know. He was trying to ham it up for his older brother, so he was probably 6 or 7 at the time, but yeah. All right, whatever. How did he know what a semicolon was? I have no idea. Anyway, that is an exceedingly good leaving group because it can leave as neutral nitrogen. And so it turns out that because of this, the benzene ring is a good electrophile. And you can do things like replace that the diazonium group with a nucleophile, such as OH, to get this molecule, which is called a phenol. Now, interestingly, the mechanism is not SN2. SN2 requires backside attack because the nucleophile has to attack the antibonding orbital between carbon and the leaving group, and that's 180 degrees away from the carbon leaving group bond. If you know anything about molecular geometry with benzene, that antibonding orbital would be pointing right to the middle of the benzene ring. In other words, you can't get there from here. The nucleophile can't do that. So you need a different mechanism, and what it's going to be is an addition mechanism followed by an elimination step. So lone pair on the oxygen on the nucleophile will attack the carbon that has the leaving group and will break a pi bond, and electrons will move out onto the adjacent carbon. Our intermediate is going to be no longer aromatic. It's going to have an sp3 carbon bonded to both nitrogen and oxygen with an adjacent negatively charged carbon. That negative charge is stabilized by resonance, but the intermediate is no longer aromatic, so that's an uphill step. But the negatively charged oxygen can kick down in a subsequent elimination step that reestablishes aromaticity and kicks off the excellent leaving group, thereby giving just the phenol. You can tell that nitrogen's an excellent leaving group because we are literally swimming in an atmosphere of mostly nitrogen and it's just sitting there not doing anything, okay? And so that's why this chemistry works. So now what we're gonna do is there's a couple pages in your book with a ton of new reactions. It's all the same reaction, we're just mixing and matching nucleophiles. So I'll take you through a list of things that these nucleophiles can, that the aryl diazonium salt is good for based on different nucleophiles. For example, if you use copper bromide or copper chloride, I'm not sure what the copper is for. It may be important and play a role that I don't understand, but effectively you're just using Cl- or Br- as the nucleophile. I wouldn't have asked you to predict that you would need copper, but if you see copper bromide used with an aryl diazonium salt, then it would make sense. Then you should be able to predict what these products are. And you would get, sorry, that plus is meant to be an or, depending on whether you use copper bromide or copper chloride. This reaction is called the Sandmeyer reaction. Sometimes organic chemists like to know names of reactions, and that name is inconsequential, but if you go on in organic chemistry, you may hear some things about it. Now, we have alternative ways of making aryl halides, right? Why don't we just do aryl halogenation from chapter 20? The answer is you probably would, but there may be some times where to get the right regioselectivity, this would be the right choice. And there are some practice problems in the study guides and problem set that'll give you some exposure to that kind of thing. Another nucleophile that you can use gives us access to a product that we haven't been able to do. What if you wanted iodide on the ring instead of bromide or chloride? We don't really have an iodination electrophile for electrophilic aromatic substitution, or rather we didn't have one in chapter 20. But if you make the aryl diazonium salt, you can then use iodide, I- as the nucleophile, and then you can replace the leaving group with iodide. Same thing for fluoride, though the reagent here is going to frustrate you. It's not going to make sense, and I actually don't really know the mechanism. The reagent of choice is hydrofluoroboric acid. If you were to try to draw that reagent, it's got 4 fluorines attached to boron, and then the hydrogen's got to go somewhere, and the only other place is on one of the fluorines. As to how F- acts as a nucleophile from there, I don't know, and I really don't know what to tell you. You can look it up if you want to know more. I don't actually care enough to know more. So this will replace basically using F- as a nucleophile. You don't need to know that mechanism, but that's the only way we currently have from the text so far to put fluorines on benzene rings. Why would you want to do that? It turns out there's a lot of drug molecules that have fluorines on benzene rings, aryl fluorides, and so having that as a starting material is having this as a being able to make aryl fluorine bonds is pretty useful. The last one, let's see. Oh no, there's 2 more. There's 2 more which are useful in synthesis but are likely to frustrate you. One is copper cyanide. Again, why you need copper is unclear to me. Cn- is the nucleophile. And you can make this molecule, which is called benzonitrile. Now, your text loves synthesis because the author of your text is a synthetic organic chemist. And so your text uses this as an opportunity to remind you of things that you can do with nitriles. Now, in chapter 15, we discussed these briefly. We didn't really learn the mechanisms, and I said at some point you're going to need these in synthesis questions. We'll revisit it at that point. This is that moment. So what I'm going to do is point you to chapter 15, and the page in the book is page 724, and this will summarize the various things you can do with nitriles. One example that I'll show you here is called nitrile hydrolysis. This is maybe the most useful one. You can use H3O plus and water. You can also do it under basic conditions. But this will hydrolyze the nitrile and replace the 3 carbon nitrogen bonds with 3 carbon oxygen bonds. And then you can get this benzoic acid or this carboxylic acid. There are other things you can do with nitriles too. They are electrophiles. You can reduce them with lithium aluminum hydride to get amines. You can reduce them with diol to get aldehydes. You can react them with Grignard reagents to get ketones. They're not the most important reactions, but you may need some of them to do some of the problems on the study guide and the problem set. So if you get stuck on something, consider looking at those reactions from chapter 15 to refresh your memory. In particular, if you need to do a synthesis and you need to have made a carboxylic acid, this is one way to do that, and it may be easier and more selective than other ways. Okay? I won't say too much about that because we need to do some other things today, but I did want to give you the heads up on that. The last reaction is going to be the most frustrating one because it's going to look pointless. So the reagent here is called hypophosphorus acid. And basically it is a hydride delivery reagent. It doesn't look like it, but it is a reducing reagent. If you look at its structure, it, I think, is this. And you could imagine that if I deprotonated this oxygen and this oxygen were negatively charged, maybe electrons could kick down and kick off H- as a nucleophile. Now, H- is a terrible leaving group, but you've seen hydride delivery reagents before, like sodium borohydride, lithium aluminum hydride, NADH. Why aren't they using any of those here? I don't know. I looked it up and this method works, and so people use it. But it replaces the diazonium group with a hydrogen. Now, you're going to think that's the most boneheaded thing you could possibly do, because that's what we started with. So we got all this trouble to make the aniline and then the diazonium ion, and then you're like, okay, back to benzene, and you're just stuck in a loop. Are you going to do that forever? That's the new circle of hell, right? Is being forced to make benzene again and again and again via the same method, right? Don't worry, I'm not a consultant for hell. They don't ask me what I think should be done there, all right? Anyway. Some of you disagree, having taken my exam, right? All right, whatever it's like, it can't possibly be worse than this. So let me show you, it's actually good for a few cute synthesis problems in the text, making things you could make in no other ways. But look at what it does. Via this method, you could go through a path that has either a nitro group or an aniline. You could do other chemistry, and in the end, you could make the aniline disappear. So this series of reactions, diazotization followed by hypophosphorus acid, is the make an aniline disappear reaction. So it's sort of magic, or at least has that appearance. Now, why would you ever want to do it? Let me give you just one or two examples. Again, not the most important thing. We don't want to spend forever on it, but a little bit will maybe show you the utility. Supposing you wanted to make that 1,3,5 tribromobenzene, where all of the bromos are meta to each other. No way to do that through aryl halogenation, because bromos are ortho and para directors. So you can get the one on, but if you try to do the next one, you're not going to get the right regioselectivity. So what you need is a directing group that's strong enough to get the bromos ortho and para to itself, and then you need it to poof, disappear, and be replaced by a hydrogen. So here's the strategy. You start with the aniline, and you do aryl halogenation. Now, at one point, I put an asterisk by aryl halogenation. We glossed over something in chapter 20 that I'm not going to hold you responsible for, and that is that anilines are so electron rich that you often see over-halogenation of just aniline. And if you want to avoid over-halogenation, there's two things you can do. You can leave out the Lewis acid catalyst and just use Br2 and get the monobromide, or you could acylate the nitrogen, turn it into an amide, and then have less of a problem. I told you that in chapter 20 you were free to use this reaction on anilines and only get the monobrominated product with the one bromo on. But in reality, often you have problems with over-halogenation, so it's possible, using an excess of bromine and using the Lewis acid, to get in a single step the bromos on all possible ortho and para carbons. Okay? So from this point on, you are free to use this reaction as though it works to put just one on, but if you need to put 3 on, you're also free to use it that way. We're glossing over that little detail. It's not important. I hope you can live with that. Okay, so now the bromos are all on the right carbons. They're all ortho and para to the aniline. They are meta to each other. At this point, we do the disappearing reaction, which is we do the diazotization with sodium nitrite and HCl. I probably should have made that arrow a little smaller because I want space to show the intermediate. So sodium nitrite and HCl turns the N group into the diazonium group. All of the bromines are still there. And then poof, H3PO2 replaces the diazonium group with a hydrogen. I'm sorry, it's leaning to the side. Okay. Yes, go ahead.
What would happen if you did the first step of the reaction without the aniline?
If you did the first step of this here?
Yeah, like if you added the bromine.
Oh, if you just if you just did bromine and the Lewis acid catalyst to the benzene ring, that would generally work to put one bromine on. Could you put a second one on? It would be harder because though bromine is an ortho and para director, it also makes the benzene ring less nucleophilic. So you could do it, it just wouldn't be that efficient. Yeah?
I thought we couldn't use the FeBr3 when there's an NH2 on it.
Right, that's a okay. If it's for Friedel-Crafts that you can't use the AlCl3 because it binds to the aniline. Apparently, you'd think it would be a similar problem for the FeBr3. Apparently, it's not that. So, yeah, good question. What else? All right, there is a practice problem from your study guide. I don't want to say too much about it because I want to save time for some other important stuff, but I'll just refer you to problem 22.62, in which they tell you to start with the aniline and end up with the Br and a methyl group. And the idea here is you could think of ways to do this not involving aniline, but they want you to practice from the aniline. And so the idea is you're going to use the aniline to get the Br and the CH3 group in the right place, and then you're going to make the aniline disappear. Okay, I would like to, if you want to see a run through of that problem, you could fast forward through the 9 a.m. lecture where I did have time for it. But at this point, I'm afraid I'm not going to have time for the more important stuff, so I'm just going to gloss over that. The solution's in your text, and the full walkthrough's in the 9 a.m. lecture if you want to see it. Okay, the second thing that diazonium ions are good at is as electrophiles in as electrophiles in electrophilic aromatic substitution reactions. So let me give you an example of that. Here is an aryl diazonium ion, and then here is going to be a nucleophilic benzene ring. In this case, it's a dimethyl aniline. Now, you've already learned that aryl diazonium ions are electrophilic at the carbon that's bonded to the nitrogen leaving group. They are also electrophilic at the nitrogen on the end, because if a nucleophile were to attack here, you would break one of these pi bonds and that nitrogen could become neutral with a lone pair on it. So diazonium salts are electrophilic in two places, one on the carbon and the other one on the nitrogen on the end. When the nitrogen on the end gets attacked, then that's what what I'm going to show you now involves attack on the end of the nitrogen. So we're going to do an electrophilic aromatic substitution reaction using this electron-rich benzene ring as the nucleophile. We'll look at that electron-rich benzene ring and we'll note that the dimethyl aniline group is an ortho para director. So we're going to expect it to attack the electrophile on the ortho or para carbons. Let's just show the para attack for now. Pi bond attacks the nitrogen, breaking the nitrogen-nitrogen pi bond and creating a new carbon-nitrogen sigma bond. Here's what that intermediate looks like. Those nitrogens that used to be sp hybridized are now sp2 hybridized. Here is the new bond we just formed. And then over here, the intermediate's going to look exactly as you would expect for an intermediate from an electrophilic aromatic substitution reaction. And in the next step, a base, a counterion of something, it doesn't need to be a strong base, will remove this proton and restore aromaticity, creating the azo compound. And the key feature of the azo compound is this linkage between this doubly bonded two nitrogens that connects two aromatic rings. Okay? So that's the process. Yes?
On the electrophile, is the nitrogen just that much more electrophilic than the carbon, which is why it attacks there? Or would there ever be like a mixture of it where it could go to the carbon?
Yeah, that's a really good question. Could the benzene ring nucleophile attack the carbon? That seems reasonable. If it doesn't happen, you could hypothesize that sterics might make it hard for the benzene rings to get close to each other. The product of that would be two benzene rings directly bound to each other. Those products are known. They're called biaryls, but I don't think they are made through that chemistry. So I don't know whether it works or not. Your text doesn't show it. It's a good question. Yeah?
All the examples I've seen of an azo compound, it adds para. Are there situations in which it adds?
I think you would expect it to add, the question is it always going to add para, or you would expect to get a mixture of products. It's possible that sterics make the ortho product a little bit tighter, but I don't know. In fact, if you look at some of the dye molecules that I showed you, there's evidence, at least in some of them, that it's okay to have a group ortho to the azo group. So yeah, I don't know. You would presumably get a mixture. Okay. So I'm calling this an azo coupling reaction because you're bringing two things together, two separate pieces together. And this is an example of what's called a convergent synthesis, meaning we can make all kinds of azo compounds by doing things to this ring first and this other ring also, and then bringing them together at a late stage. And that will allow us to make a wide variety of azo molecules. Let me give you an example of a synthesis that we could go through to get one of these azo dyes. So here we go. The two benzene rings, the azo compound. And then over here, I'm going to put a nitro group. And then over here, let's put a methoxy group. All right. So in synthesis, it's often good to begin with the end in mind and even begin at the end by thinking about what's the last step you would take. Now, before we do that, I want you to think about whether it's a good idea to do the azo coupling reaction first and then get the other groups on the benzene ring, or to get the other groups on the benzene ring first and then do the azo coupling. What challenges do you see if we were to try to put a nitro group on this molecule? Go ahead.
But also, if we're trying to get it ortho on that one benzene ring, then it might just appear ortho on the other if that methoxy is not already there.
Right, you've got selectivity problems, right? You've got selectivity problems on either side. You can't, because those benzene rings are identical, what you do to one is going to happen to the other. Now, you could try to play around with, oh, what if I only add half a mole of nitro for every mole of product I have? Would that work? And the answer is probably not well. So there's a better way. And the idea is we're going to modify the benzene rings first, and then and only then bring them together at the late stage. So the azo coupling step will happen last. So what I'm proposing is that instead of that approach, we take a first step backwards and draw what the diazonium electrophile would be and what the nucleophile would be in this electrophilic aromatic substitution reaction. And if you have a choice and you look at your azo compound, if one of the benzene rings is more electron rich than the other, you should use the electron rich benzene ring as your nucleophile and the electron poor one as your electrophile. So which of these benzene rings is electron rich?
The left one.
Oh wait, your left is the same as my left. Right, okay, yes, methoxy. That's the electron donating group, so that means this benzene ring is electron rich. So that means you want to use this portion as your nucleophile, and then you're going to use this portion as your diazonium ion electrophile. So let's just think a step backwards. Your nucleophile is just going to be methoxy substituted benzene. Your electrophile should be this diazonium ion that has a nitro group ortho to the diazonium group. Okay? Now we've split the molecule up into two different parts. This is the bond that's going to be made in that electrophilic aromatic substitution reaction. Now we have a simpler synthesis problem. Now all we have to do is figure out how to make the nucleophile and the electrophile. So we haven't ever put a methoxy group on a benzene ring before, but we just barely learned how to put an OH on a benzene ring. Yeah?
Are we going to see the azo group on the nucleophile?
No, the nucleophile doesn't have the azo group. Yeah. So look at that reaction. The azo group is only on the electrophile. Yep. So we have learned how to make phenol. So you could imagine making the methoxy group via an SN2 reaction with phenol. Probably need a base to remove the proton on the OH group. And then you could alkylate that OH group to make the methoxy group. We've just learned today where we get phenols from. You can use the diazonium ion, which I'm going to just abbreviate as N2 plus. No, I don't like that, sorry. Why am I going to change the way I've been drawing it all of a sudden? So you can get the phenol from the diazonium ion, which you can get from the corresponding aniline, which you can get from benzene, right? We know how to do that. Getting that aniline from benzene is nitration followed by reduction. Getting the diazonium ion from aniline is that new diazotization reaction involving sodium nitrite and HCl. Okay, do you see that connection? We're walking our way back. Okay, how about the electrophile? Again, we could get that electrophile by diazotizing. Now we need to think just a little bit strategically. We could obviously have, would it make sense to say, oh, I want to get that aniline from this starting material? What's the problem with that? Selectivity, yeah, you modify one, you're going to modify the other. So that's a bad strategy. Probably we need to do, at this stage, the previous reaction would have been nitration. So we start with the aniline, we get the nitration. Once we're back to the aniline, we've already solved that problem. The problem probably would have said, make everything from benzene. And this is the other organic chemistry circle of hell in which you are stuck on a desert island forever, but you have infinite access to an organic chemistry lab, and you can make whatever molecules you want, but you have to start with benzene. That's the rule, and you get to do that forever. So anyway, this is an example of the kind of synthesis problem that you could do. All right, questions about that? Go ahead.
For our nucleophile creation, when we're adding OH from the why can't we just add like sodium?
Methoxide? Yeah, I think that would work too. The question is, can I sidestep all of this stuff by just using CH3O-? And I think so. I think that would work. I've looked at the solutions manual in your text and they don't do it that way. That could reflect something your text author knows, which is maybe somebody's tried it and for whatever reason it doesn't work well. I would call that good. Yep. All right, others? All right, in the last couple minutes, I want to tell you a story of how azo dyes led to a class of antibiotics. In 1935, a German physician was working for a dye manufacturer, and his daughter got ill with a streptococcal infection. Now today, if you're ill with a bacterial infection, you go to the doctor and they prescribe antibiotics. And hopefully, if you don't have MRSA or some other horrible antibiotic-resistant strain, you get better pretty quickly. She was hovering on death's door. He worked for this German dye manufacturer and had access to this dye, which is now called Prontosil. And as you know, people had already been testing whether dyes can kill bacteria and pathogens using, because of what Paul Ehrlich did. So it was known that this Prontosil inhibited bacterial growth in mice. So he did something that is probably today considered unethical, but it did save her life, and that is he brought some of the dye home and he gave it to her. Now, you never ever do that as a scientist. You never give a molecule that you've made hoping that it's going to save somebody's life. There are ways to do this. You have to do testing. There's internal review boards. There's clinical trials and all of this stuff. But it was his daughter. What was he going to do? And she lived, and so then a bunch of research got started into, can we use this as a drug? It turns out that the reason, and he ended up winning the Nobel Prize, okay? That is not the way, that's not the way Nobel Prizes are awarded today. You have to do exhaustive testing for safety. It turns out the reason this molecule worked was not because of the azo molecule itself, but because in biology, it gets, in a biological system, this gets metabolized to the active molecule, which is this molecule called sulfanilamide, or a sulfa drug. And this discovery happened just immediately before World War II, and sulfa drugs were used widely as antibiotics in World War II. And they have been replaced largely by other things, but they remain in sort of our drug arsenal for treating bacterial infections. There's more we could say about that, but I think that's about enough today. You've had a test week, so get out of here. I'll see you on Monday.